So this one might look a little scary, but it should be a lot easier than alternating series. So geometric series test. Just to prove convergence, the big idea is it's called a geometric series because you can visualize it with geometry. Here I ran out of space, but imagine there's a square that is length 1 on all sides. So that would be the first term because that's our a value. And then we'd get 1/2 on either side, and then we'd add that up, and then we'd just keep adding it. So what we'd know via this is that there's no possible way for this value to be like less than, or when we're doing this, since we're finding the area of squares instead of just adding lengths together, um, this, if we added all the areas up, would give us the square root of the sum. Obviously, I stopped at 1/16. You would have to keep going. But visually, you can see that the squares do not exceed the value of 2, because it would be 1 times 1 for the area of this entire square, and then 1 times 1 for this entire square. So obviously, the area is less than 2, so the actual sum is less than the square root of 2. If something is less than the square root of 2, it cannot be infinity, because the square root of 2 is a finite number. So just visually, obviously this doesn't extend until infinity. It extends until the square root of 2. There is a formula, though, for the sum of a geometric series. You've probably seen it before. It is S equals A over 1 minus R. So that is the sum, but that's a little bit nebulous. It seems meaningless. Doesn't really make sense for it to be something like that. But it's a pretty simple algebraic proof. There is S of n, and here is how it goes. You have to make sure that it ends at n minus 1 instead of n, since we start at n equals 0, and that just simplifies some of our math. So here we have these values, and let's try multiplying it by r. So if we multiply it by r, what we'll get is a naught r plus a naught r1 plus a naught, or no, that won't be r1. This will be r1, this will be r2, this will be r3, then all the way to a naught rn minus 1, and a naught n minus 1, and then a naught n plus a naught r to the n. So what if we subtract Sn from r Sn? If we do that, then we'll get, we'll have this a naught term left over in the positive, and in the negative side, in the r Sn side, we'll have negative a naught r to the n. So now, if we just do a little bit of factoring, you can easily see that S of n times 1 minus r equals a naught minus a naught r to the n. So this is just for any sum. This is for any sum of length n. Actually, first I'll do the general formula for finite sums, and then I'll take a limit. So we'll get S of n equals 1 or not that side, a naught minus, or I'll factor it on this side too, a naught 1 minus r to the n over 1 minus r. Now, if we take the limit as n approaches infinity of S of n, we'll get this going to 0, and then we'll have a naught times 1 minus 0. That'll just be a naught on the top, and then on the bottom there's no n, so we'll just get 1 minus r. This is how we get the sum formula for a geometric series. One thing I didn't talk about is with the geometric series test, the absolute value of r must be less than 1, Alternatively, you can say it like this. I decided not to prove that through any visual means, since it's very simple to prove with nth term divergence, unless this value is unless this value has an absolute value that's less than 1, it won't pass nth term divergence, since it'll exponentially grow instead of exponentially decay to 0. It needs to go to 0 to converge. Yeah. Yeah, I always was confused by the sum formula, but after just like thinking through it in terms of actually just addition and subtraction, it's pretty clear why it's pretty clear why these last two values are the only ones that matter, and then the last value doesn't matter at all when you go to infinity. So really only the first value matters, and then the actual rate.